Now let's propagate uncertainty using mixed operations. So in this case, we will have an addition-subtraction event, and we'll also have some multiplication-division. How do we handle that when we're propagating error? So a typical thing to have is a calibration curve. And so I have a linear response up here. So I have some variable that we measure related to perhaps a concentration here. Here's my slope, here's my intercept. I have uncertainties in each of those, and I have uncertainty in the value that I measured. So let's determine what the value of x is with the uncertainty associated with it. So again, one of the first things that I like to do is actually just solve the problem without doing all of the uncertainty bits with it. So then I can see what I need to do and which formulas to use and when I'm doing the uncertainty propagation. So here we go. We've got 64.71, and I'm going to plug that in for y, and then I'm going to solve for x. So I'm going to do this rather quickly. I'm going to subtract this over to that side. So minus 0.72. And then I will need to divide by my slope, which is 28.3. And this will calculate the value of x. Now, one thing that I want to do though is I actually want to keep track of my intermediate values. So I'm not going to just immediately simplify this down to one number. I'll show you what I mean. I'm going to do this subtraction separate and keep that value, keep track of that value. So I've done the subtraction. Now, what this does is you'll notice that I've done a subtraction first, then I'm going to do a division. That lets me know that I need to take these two values, the uncertainty with them, and propagate the error. Then I will propagate the error here. So you'll notice this is a subtraction, so I'll have to use the subtraction formula. This is a division, so I'll have to use the multiplication division formula for this propagated error. And you'll know that I need to have the magnitude of the measurement to put in this, the multiplication division formula, because I need to use relative errors. That's why I need this intermediate value. Now, if you're doing this all out on paper, you may forget that you need the intermediate values, but if you're doing it on a spreadsheet, you might want to calculate just one step at a time so that you have these intermediate values to employ in the uncertainty calculations. Yes, okay. Now this comes down to 2.26113. Now, let's propagate the error so that I know what the uncertainty is in my 63.99 value. So to do that, I need the uncertainty for the 64.71, and I need the uncertainty for the 0.72, and I will propagate the error between those two. And since it's subtraction, I use the absolute error, so that is 0.06 squared plus 0.03 squared, square root of that, and this is 0.06708. And I'll often leave extra digits on there just because I know the calculation's not done yet. I'm going to use that value up here. So now I know that this is 63.99 plus or minus 0.06708. Now I'll take that uncertainty and calculate the relative uncertainty for it, calculate the relative uncertainty for my 28.3, and then run it through my calculations. So here we go. And this is going to be divided by my 63.99. Squared plus, and then 0.4. So it looks like by far this is going to affect the uncertainty of the measurement quite a bit more, just because this is a much larger number and that's a smaller number than that. So this is really where our error is coming in from in the measurement. And it's useful to note that, to just see like, oh, my error is coming from this location, and that might instruct us on how to improve our analysis or our measurements. So I got 0.01417 for that, and that is relative error again. So I will need to take this number, multiply it by my x value to get it back into absolute uncertainty so I can report it as plus or minus something. So I'll do that really quickly down here. Times 2.26113. And I got 0.032. That's my absolute uncertainty, because again, relative uncertainty times the magnitude of the measurement that it's associated with will get us back into absolute uncertainty. So now I can write my x result with the appropriate number of significant figures. So I have this, that's 0.03, because we'll round this off. So I'm going to write 3 digits here, or 2 decimals, 3 digits. Again, I'm doing that because the error is starting with that digit right here. And that's why I actually rounded off. Now, you may have used significant figures, especially in general chemistry or maybe some physics classes, but the real uncertainty or the real significant figures, determining factors, is when you propagate the error or run some kind of statistical analysis on it to determine where my error starts. So in this case, it really doesn't matter that how many digits we would expect from significant figure rules. Now in this case it does end up matching up, but it often has some variability there where you might lose a so-called significant digit just from the fact that there's quite a bit of error along the way. Now, it's not always the case, but it could happen. And we should propagate the error to determine that. And one of the things that significant figure rules doesn't tell you is normally we would assume that, oh, the 6 right here is significant, and it is, but we might think that it's just 2.26 plus or minus 0.01, right? There's variability in this last digit. Well, our significant figure rules didn't tell us how much variability is there. And in this case, it is significantly more than 0.01, or varying up or down 1 digit, which often is kind of what we think. But this just gives us a little bit clearer picture about what is actually happening when in our measurements and how error in one piece of the measurement may affect another. So this is how to propagate error in mixed operations. You just do them step by step and then combine in the end however you need. And remember, you may need to convert from relative uncertainty to absolute uncertainty before we report the measurement.